Very good morning, friends. We were dealing with retrosynthesis. As we know, retrosynthesis means it's the reverse of synthesis. Here, we conceptually cleave the molecule into smaller fragments to get the starting material and the reagents. The preliminary requirement for retrosynthesis is that we need to have a profound knowledge of basic organic chemistry. Means we should have the knowledge of types of reactions, the conditions of the reactions to be followed or to be arranged to complete the reaction, and we also should have the knowledge of mechanism of the reaction. For example, in functional group addition or functional group interconversion, the major functional groups we add are either electrophiles or nucleophiles. And in electrophiles and nucleophiles, in aromatic substitution, we follow. Now, how to identify the synthons? How to identify the suitable reagents for those synthons? Further, when we break the molecule, which fragment should get a positive charge or which fragment should get a negative charge? And we have to add. And for this thing, we need to have the sense of polarity. For example, if I take paramethoxyacetophenone, that's nothing but hawthorn blossom perfume. I want to synthesize this target molecule. That's why I break the molecule over here. I can, if I break, there is carbon-carbon bond breakage, and in one I have given benzene the minus charge, the carbonyl group over here positive charge, or I can give positive charge over the benzene ring system and negative charge onto the carbonyl system. Which is right? As we know, benzene is electron rich. It is sensible to give negative charge onto the benzene ring. To assign negative charge onto the benzene ring is the right choice. And carbonyl carbon, the oxygen is attached to the carbon, and we know that oxygen is more electronegative than carbon. As it is electronegative, it has the tendency to pull the electrons, and that's why it makes the carbon adjacent to this electronegative group positive center. That's why it is sensible to give positive charge onto the carbonyl carbon, not the negative charge. That's why we should have the knowledge or the sense of polarity, sense of electronegativity. That's why we can give minus charge to the benzene ring system and add positive charge, assign positive charge to the carbonyl carbon. These two are the synthons, and the reagents that can be used for getting the synthons are anisole and acetyl chloride. I take anisole and treat with acetyl chloride, and for this two to react, and the position which this acetyl group attaches depends upon the functional group attached onto the benzene ring. If benzene ring has an electrode donating group, then it activates the ring system. Once it activates the ring system, it will be orthopara directing. Here you see here, methoxy is group is electron donating group. As it donates electron, it activates the ring system. When it activates the ring system, it will be orthopara directing. And for this reaction to occur, we need a catalyst, that is a Lewis acid like aluminum chloride or FeCl3 or zinc chloride. And this reaction is called Friedel-Crafts acylation. What all it indicates? It indicates that we should have the knowledge of the reagents. We should have the knowledge of the type of reactions. We should have the knowledge of catalysts. The profound knowledge of organic chemistry is a must for its knowing the synthetic route. This is the preliminary requirement. If we do not have the basic knowledge of organic chemistry, retrosynthesis cannot be successful. For example, if I take to add various functional groups in the aromatic compounds, I take an aromatic compound. The simplest example is benzene ring. I treat with an electrophile. We know that benzene is electron rich and that's why it can undergo electrophilic substitution reaction. The H plus in the benzene ring is replaced by E plus. I'll get corresponding E substituted benzene ring system. And to get this molecule, the retrosynthesis means I have to break the carbon-carbon bond breakage over here. And I will get E plus and C6H5 minus. When I want the synthon E plus is R plus, what is the reagent I should use? I should use alkyl halide. Alkyl is combined with halide group. Halogen being electronegative pulls the electron, renders this R positive, and that's why I get R plus as synthon. And RBr I take and treat with benzene, and I need Lewis acid as a catalyst along with this alkyl halide. And this reaction is called as Friedel-Crafts alkylation. Instead of alkyl halide, I can also use alcohol. Instead of Lewis acid, I have to use mineral acid, which can donate H plus. As we know, the acid is a proton donor. It donates this proton. Oxygen in the ROH is in sp3 hybrid form, and that's why it has two sets of lone pair of electrons, and these electrons are protonated by this H plus. It becomes ROH2 plus. To satisfy this positive center on OH2 plus, the bond between the R and O breaks, and that electrons are taken away by oxygen, giving R plus. Instead of this alkyl halide, I can also use alcohol. For the same reaction, I can use different reagent and get the same product. This you can appreciate now, the knowledge of basic organic chemistry, the knowledge of basic types of reactions, and the knowledge of the mechanisms of the reaction. If I want RCO plus, I can use RCOCl as the reagent and I can use Lewis acid as we have seen in the previous example. And this reaction is called as Friedel-Crafts acylation. I want NO2 plus to be added. For this synthon, the reagent used is concentrated nitric and sulfuric acid. Nitric acid and sulfuric acid reacts to regenerate nitronium ion, and the nitronium ion reacts with the benzene ring system, and this reaction is called as nitration of benzene. Similarly, halogenation, I take Cl plus as the synthon. What should I use? I should use chlorine along with Lewis acid, and this reaction is called chlorination. If I want bromine plus to be added, I use bromine and Lewis acid, and this is bromination. If I want sulfonate group to be attached, I'll treat with concentrated sulfuric acid, and this reaction is called as sulfonation of benzene. Now, you may appreciate the knowledge of reactions, the knowledge about the reagents which are available, and how we can choose the reagent for a particular synthon. We can choose the reagent if we have the knowledge of the reagents available. And we can do the reactions if we have the knowledge of the types of reactions, mechanism of reactions, and the conditions of the reactions. Sometimes we know that directly functional group addition may not be possible. As we have seen in benzocaine synthesis, the amino group I cannot directly attach to benzene because the NH2 minus and benzene is also electron rich, and we know that like poles repel each other. That's why in that case we have to go for fragment group interconversion, that we call it as FGI. Sometimes we need to do fragment group interconversion, and that fragment you have to introduce and then convert into the one which we are in need. I want X I cannot directly add. That's why I add first Y and then convert into X. If I want X is NH2 I cannot add directly to benzene ring system. That's why first I will add nitro group, then reduce it by using hydrogen and palladium, and I'll get amino group. Fragment group interconversion is necessary in many of the cases when directly the functional group cannot be added to the particular system. The above knowledge about this is also a necessity for retrosynthesis. If I want an alcoholic group to be attached CHOH, or I add COR by Friedel-Crafts acylation and then reduce it by using a mild reducing agent like sodium borohydride. If I want CH2R, I can directly add alkyl halide, but there are chances of rearrangement. In that case, to avoid that, I add acylate it and then reduce it to alkane group by using a stronger reducing agent than the sodium borohydride like zinc and amalgam to get an alkyl group. If I want COH group, as we have seen in benzocaine, COH, CO2 is a very weak electrophile and its For that to react, the benzene should have strongly electron donating groups like OH. Then only it is possible. That's why when it is not possible, I'll add methyl group by Friedel-Crafts alkylation and then oxidize it to carboxylic acid group by using potassium permanganate as an oxidizing agent. Or instead of adding methyl group, I will add cyanide group, and this if I hydrolyze in the presence of concentrated sulfuric acid, cyano group gets hydrolyzed to carboxylic acid group. Yes, the knowledge of reactions, the reagents, and the interconversion conditions required, all these are the basic necessity for doing the retrosynthesis. If I take BHT, butylated hydroxytoluene, this is used as a antioxidant and a food preservative. I break the molecule at this tertiary butyl and benzene junction and I get synthons. It is sensible to assign minus charge to benzene ring as it is electron rich and positive charge to the alkyl ring system. And the reagents which I can use is tertiary alkyl halide or tertiary butyl chloride and the paracrisol. OH is strongly donating, ring activating and ortho para directing. As para is already occupied by methyl group, the incoming group will come at the ortho position and I will get the butylated hydroxytoluene. I can use cresol and tertiary butyl chloride as the reagent to get butylated hydroxytoluene. Or instead of this, I can use an alkene. And in the presence of acid, this gets protonated and positive center over here, and that excess electrons attack on this. Alternative to Friedel-Crafts alkylation. The same butylated hydroxytoluene can be obtained by using two different reagents. One is a tertiary butyl chloride, another is a tertiary butene. If I take isobutyl benzene and I have to prepare this, I'll break over here. I'll get benzene with minus charge and the tertiary butyl group. This has the positive charge. These are the synthons or the fragments. And to get these synthons, I can use benzene as reagent and the isobutyl chloride as another reagent. These two can undergo Friedel-Crafts alkylation. But however, there is possibility of the rearrangement. Once this break, AlCl3 reacts with chlorine to give AlCl4 minus and the plus over here. This becomes the primary carbocation. Once there is a primary carbocation, there is adjacent carbon over here. This will take the electrons CH3 minus the CH3 group along with its electron pair moves onto this positive center, and it gives rise to a secondary carbocation. Before benzene reacts with this primary carbocation, it gets converted into secondary carbocation, and I get the rearranged product than that of isobutyl derivative. And another drawback of this Friedel-Crafts alkylation is the product that is formed can undergo further alkylation and give polyalkylated product along with this isobutyl benzene. That's why to avoid these things, I will do fragment group interconversion. This alkyl group, whatever is here, I'll convert into interconvert into acyl group and then break the molecule. I'll get corresponding benzyl phenyl and the corresponding acyl as the synthon, and I will use corresponding acid chloride and benzene as the starting material. When I use this undergo acylation first, then reduce it by using zinc and amalgam to get isobutyl benzene. Now I have added the formation of the other type of product because of the rearrangement, and I have added the polyalkylation. This is another example to show that the knowledge of reaction not only helps, but also we should know the limitations of the reactions and how to overcome the limitation. We should have the knowledge that helps in retrosynthesis. Not only the electrophilic aromatic substitution, we can also carry out nucleophilic aromatic substitution under special conditions. The diazonium chemistry we follow, I have to add X. I can dissociate into benzene and X minus. The X here is in the nucleophile, and nucleophilic addition or nucleophilic substitution is difficult because benzene is electron rich and X minus nucleophile is also electron rich. It repels each other. In that case, what should I do? I should increase the positivity of the benzene ring system. How to do that? For that, instead of X minus, I add NH2. I'll take aniline, and this aniline I'll make it to undergo diazotization. So I do diazotization by using sodium nitrite and HCl. They two react together to give nitrous acid. Nitrous acid combines with NH2 to give corresponding benzene diazonium halide. Nitrogen is electron deficient. To satisfy this electron deficient nitrogen, the electrons between the carbon and nitrogen breaks, and these electrons are taken away to the nitrogen and renders this carbon on the benzene ring positive. That's why the X minus, as this is the positive center, as the electrons are taken away by nitrogen, the X minus can attack on this positive center, and I can achieve the required aromatic nucleophilic substitution with the loss of nitrogen. If I need X OH, the reagent X minus, what should I use? Water. If I want all OR, I'll use alcohol as a reagent. If I want cyanide, I'll use cuprous cyanide as a reagent. Cu plus Cn minus. Cn minus can attack on the positive center, liberates nitrogen. I'll get corresponding benzonitrile. If I want chlorine to be attached, I use CuCl, cuprous chloride. If I want Bar minus to be attached, I'll use cuprous bromide. If I want iodide to be attached, I'll use potassium iodide. If I want aryl group to be attached, I'll use another aryl group. I can prepare biphenyls. If I want H, I'll use phosphorus acid. Now, the knowledge of diazonium chemistry has plays an important role in achieving this. This reaction of this diazonium chloride with cuprous halides or cuprous cyanide is Sandmeyer's reaction. Yes, you can appreciate the knowledge of chemistry requirement for retrosynthesis. Not only the knowledge, and we should know which reaction to be carried out first and which reaction to be carried out next. That is the order of events to be followed. And there are guidelines given for that. And that will be the subject of discussion for the next class. Till then, have a nice day. Thank you.